In this video tutorial, we will discuss the different types of chemical reactions. So if you recall, during a chemical reaction, atoms are rearranged to create new structures. Just like Lego blocks, we have to disassemble the old molecule before we can reassemble it into a new molecule. The process of breaking the old bonds requires energy, while the process of forming the new bonds releases energy. Now, every chemical reaction requires you to break the old bonds before you can form new ones. You have to disassemble the old Lego structure before you can build a new Lego structure. Depending on how much energy was absorbed while breaking the old bonds and how much energy was released while forming the new bonds, will determine whether the reaction is overall exothermic, releasing more energy than absorbed, or endothermic, absorbing more energy than released. So it's like a business. Every business must spend money to make money. But if you spend more money than you make, it's not a good business. Versus if you make more money than you spend, now it's profitable. Similar to the law of conservation of mass, the law of conservation of energy states that energy can neither be created nor destroyed, it can only be converted from one form to another. And so the total quantity of energy in a system remains constant and must be accounted for. This includes energy stored within chemical bonds. Now, when it comes to the chemical reactions we'll be learning about this year, there are 4 major types with 2 subcategories in each of these. Now, the benefit of classifying chemical reactions is that if you can recognize a pattern, you can make predictions. The first pattern we're looking at is called a synthesis reaction. The word synthesis means to create or to build, and that's what's happening here. We're taking 2 smaller elements and combining them into a larger compound. X plus Y turning into an XY compound. Well, same thing. This is an X, this is the Y, slammed together, we've got XY. So let's take a look at this example. Lithium plus oxygen. So the first step is to write out the symbols for these chemical compounds. Lithium is an Li, oxygen is an O, but oxygen is one of the diatomic elements. It's not allowed to be on its own. Either it's bonded to someone else or it must be bonded with itself. Since it hasn't had a chance to bond with lithium yet, this is still the before picture, it must be bonded with itself. So I'm going to write O2. Now I can match it up with a pattern. X is lithium, Y is oxygen. So let's slam them together into XY. LiO. Unless it's a polyatomic ion, we're going to ignore the subscripts, because only when you zero sum will you have the right subscript values. Don't just carry them in. Furthermore, by convention, X is always the positive cation, and Y is always the negative anion. So always have the cation first, the metal first, then the anion, the non-metal next. Looking at lithium, I see it has a 1+ charge, while oxygen has a 2- charge. And now we can zero sum to make sure this exists. And I have Li2O. So remember, these subscripts must arise from the zero sum rule. Do not just transfer them directly from the before picture to the after picture. We are rearranging these atoms. They're no longer going to be attached the same way. They're turning into a brand new structure. And that new structure must follow the zero sum rule. Alright, I'm going to remove my rough work now. And here I have my skeleton equation. Lithium reacts with oxygen to produce lithium oxide. And that's how we use the synthesis pattern, and following this pattern, we are able to predict what product will be produced, even if I've never seen this reaction before. Now remember, this is just the skeleton equation. It doesn't contain coefficients to balance it out, so right now it is not following the law of conservation of mass. So if the question on the test or the assignment requires you to write out the balanced equation, you would have to include the coefficients in the front. Please watch my previous video on how to balance equations if you're not sure where these numbers came from. So now this is the balanced equation. But if the question only asks for the skeleton equation, then you would not need the coefficients in the front, just leave it as is. Alright, let's try another one. Magnesium reacts with nitrogen. Again, the first step, write out the element symbols. Magnesium Mg, nitrogen N. But again, don't forget that nitrogen is diatomic, so it's not allowed to be by itself. Now some students ask, sir, oxygen is diatomic. Shouldn't there be a 2 there? Well, no. Reason number 1, it would not zero sum properly, so this wouldn't exist. But reason number 2, it's not allowed to be by itself. But if you look at it over here, it's connected to the lithium. It's not by itself. It's not alone. So you did not need the subscript 2 here. But over here, the oxygen hasn't had a chance to bond to the lithium yet. It is by itself. So because it's by itself, it does require that 2. Alright, so I'm going to put the 2 there. Now we can follow the pattern. Mg is x, N2 is y, slam them together, make xy. Again, ignore the subscript 2. We have to follow the zero-sum rule for this new substance in order to determine what the new subscripts are going to be. So magnesium has a valence charge of 2+, while nitrogen is a 3-. Now we zero-sum to determine what the subscripts are. When I see a 2 and a 3, I should think of the number 6. So I need 3 magnesiums and 2 nitrogens for this to zero-sum properly. I can then erase my rough work, and I'm left with a skeleton equation. But if the question asks for a balanced equation, I would put a 3 as a coefficient in front here, and now I have 3 magnesiums, 2 nitrogens, 2 nitrogens, everything's balanced. This is now my balanced equation that follows the law of conservation of mass. But again, if the question doesn't ask for it to be balanced, you can leave it as a skeleton equation. Now another common question I get is, there's N2 here, why not Mg2? Why not put a subscript of 2 in front of the Mg? That's because magnesium is not diatomic. Only Hofbrinkel, or Brinkelhoff, whatever you memorized, is going to be diatomic. All other elements are allowed to be on their own. They are allowed to be monatomic. Now the next pattern we're looking at is called decomposition reactions. They are the exact opposite of synthesis. While synthesis builds into a bigger compound, decomposition takes a big compound and breaks it down to smaller elements. But let's start with the easy one first. Potassium oxide is heated in the absence of other chemicals. So the word absence means there's nothing there. Just the potassium oxide, so it can't react with anyone else. As such, the only type of reaction it could possibly be is decomposition, where it will break apart into its constituent elements. So let's write down the chemical formula for potassium oxide. Potassium is a K, oxide, oxygen. Don't forget to zero-sum, otherwise your grades will get KO'd. Potassium has a 1+ charge, while oxygen has a 2- charge. As you can see, this is not zero-summed, so it doesn't exist yet. We need to make it exist. Put in some subscripts. By putting a 2 subscript, I now have enough positive charges to neutralize the negative charges with the oxygen, and now we've zero-summed. K2O is potassium oxide. I'm going to erase my rough work at the top, and let's see what the pattern shows. K2O is the XY. It's going to break up into X and Y. Well, this is X, this is Y, leaving me with a K and an O separated. But what's wrong with this picture? I'm hoping that I've drilled this into your heads by now. Oxygen is diatomic, so don't leave it by itself, put a 2 there. Potassium is not diatomic, so I can leave it on lone. And now we've got the skeleton equation. If you want to balance it, it would look something like this, but you can leave it out if it doesn't ask for the balanced equation. Alright, I want you to try this one yourself. Press pause. When you're ready, press play, and we'll take it up together. Alright, so the first step is to write out the symbol. Nitrogen, triiodide, so this is a covalent compound. Triiodide, 3 iodines. Because this is a covalent compound, they will not zero-sum, so you don't have to worry about the valence charges. Because nitrogen is a 3- and iodine is a 1-, so even if you did put them in, they would never be able to zero-sum. Anyway, let's decompose it. Here's the pattern, Ni3, XY. X is the nitrogen, Y is the iodine. Breaking them apart gives you X and Y. X and Y. Can you guess what I'm going to do now? Diatomic! Nitrogen is diatomic, iodine is diatomic. Don't leave them on their own. And this is a simple decomposition reaction. Our next reaction is a single displacement reaction. Here, one element switches places with another. Because only one element is switching spots, single displacement. Now there are 2 subcategories. That would be cationic displacement. That's when the cations, the 2 positive ions, switch places. So while B was originally bonded with X, by switching the positives, now A is bonded with X and B is by itself. Whereas in anionic displacement, it's the exact opposite. It's now the negative charges that are going to be switching places. So it used to be A and X were together. Now X and Y are trading places. So now we have A and Y are together and X is by itself instead. Just remember that these new partners and the old partners must always be oppositely charged. Positive, negative, positive, negative, positive, negative, positive, negative. You can never have 2 negatives together or 2 positives together, otherwise those like charges will repel and they will not stick together. Alright, so let's try this question out. Press pause. When you're ready, press play and we'll take it up together. but essentially copper 2 is going to react with hydrogen chloride in this single displacement reaction pattern. And then try it with copper 2 reacting with silver nitrate instead. Okay, press pause. When you're ready, press play. Alright, so the first step is to write out the symbols. Because copper is multivalent with two options, 1 plus or 2 plus, I had to specify which version of copper it is. In this case, it's copper 2 plus. Next, we react it with hydrogen chloride. Make sure it's zero summed. In this case, 1 plus, 1 minus adds up to 0, so that's good. And now we switch places. Positive, switching places with a positive. Don't switch it with a negative, otherwise you'd have two positives stuck together, and that won't last very long because they would repel. So copper will switch places with the hydrogen, giving us a new partnership. It used to be H and Cl were stuck together. Now it's Cu and Cl stuck together. But watch out, make sure you follow the zero-sum rule. And don't forget that hydrogen is diatomic. This gives us hydrogen gas and CuCl2, so copper 2 chloride. But there's a problem. This reaction doesn't exist. When dealing with single displacement reactions, you must consult the activity series. Only elements that are more reactive can bump out elements that are less reactive. You can't go the other way around. You can't have a less reactive element try to bump out a more reactive element. Think of it as a VIP list. The people at the top of the list are more important than the people at the bottom list, and these guys can always bump out someone else at the bottom. So if I compare copper and hydrogen, I can see that hydrogen is more reactive than copper. So on this list, hydrogen can push out copper, but copper cannot push out the hydrogen. But here we have copper trying to push out the hydrogen when that's not allowed. So if copper is unable to push out or displace the hydrogen, there's going to be no reaction. Nothing's going to happen. In that case, we will write down NR, standing for no reaction. Let's take a look at this next question. Can copper bump out silver? Why, yes. Yes, it can. Copper is higher than silver on this list, so copper is more reactive and can bump out or displace silver ions. So silver is displaced, left alone in solution, while the copper is now bonded to the nitrate. Now don't forget to check if they are diatomic and also zero sum. In this case, silver is not diatomic, so it's okay by itself, but over here I need to have two nitrates in order for this to zero sum properly. So in this reaction, copper bumps out the silver and silver precipitates out of the solution, leaving behind copper 2 nitrate. So over here I have a copper wire that's dipped into a silver nitrate solution. The copper has pushed out the silver that was floating in the solution, and now the silver has become a solid over here. We say that it has precipitated out of the solution. Whereas over here, because copper could not bump out the hydrogen, there's no reaction. Copper remains copper, HCl remains as HCl, which is what we see on the left side. The copper is dipped into HCl, and because nothing could happen, there's no reaction. The copper could not bump out the hydrogen. It was not reactive enough. There is no reaction. It just sits there. Alright, so for single displacement reactions, you must always consult the activity series to find out who can bump out who. Only the most reactive elements can bump out the less reactive elements. Now, most activity series will give you the metallic version. They may not give you the non-metal version. So you don't have to memorize all this. It's all going to be given to you on a periodic table. But like I said, sometimes the non-metals will not be included. That's not a big deal because they're already written in order of our reactivity. So fluorine is at the top, chlorine, bromine, then iodine. So fluorine can bump out everyone else. Chlorine can only bump out bromine and iodine, and bromine can only bump out iodine. We don't have to worry about the other non-metals because they don't typically participate in single displacement reactions. It's usually the halogens we need to worry about. So again, fluorine, chlorine, bromine, iodine, fluorine, chlorine, bromine, iodine, sometimes sulfur if you see it. Now a double displacement reaction is very similar to a single displacement reaction, except this time everyone gets a new partner. Once again, the old partners and the new partners must always have opposite charges. If they have the same charge, then they will repel each other. So make sure when you switch partners that they have opposite charges. Now be careful, I have seen some students do this, it's rare but it happens, where they think, oh, double displacement, so I'll displace once and I'll displace again. Well, obviously that was ridiculous because now you have the exact same reactants as what you started off with. So that's not right. When we say double displacement, we don't mean do it twice, we mean that two compounds will have new partners, so everyone gets a new partner. Alright, so I want you to try doing these three problems. Write out the skeleton equation for each. Remember that you must always have oppositely charged partners, and by convention, the positive cation must always be the one that's first, followed by the anion next to it. Okay, so pause it. When you're ready, press play and we'll take it up together. Alright, here are the skeleton equations. So the first step, write out the chemical equation. Lead 2, so there's lead 2 because lead has two options, 2 plus or 4 plus. You have to specify which species we're talking about. So anyway, lead 2 with a nitrate ion. Again, zero sum, so I need to have two nitrates to make this exist. Followed by potassium iodide. Potassium is 1 plus charge, iodine is 1 minus, so they're already zero sum. That's good, no need for subscripts. And now we're going to switch places. So Pb is now with iodine, and K is now with nitrate. Again, make sure you zero sum. 1 plus, 1 minus, we're good. 2 plus, 1 minus, that means I need 2 of these iodines to make this stable. Moving on to this one, the positives are going to switch places. K's old partner was nitrate, now its new partner is with Cl. Sodium's old partner was with Cl, now its new partner is with NO3. Make sure everyone is zero summed, 1 plus 1 minus, 1 plus 1 minus, everything's okay here. And on to the last one, again, positive, switching places with positive. So everyone's zero summed, everyone is zero summed, 1 plus 1 minus, zero summed on this side as well. It all looks good. Now, in grade 10, that would be the end of that. But in grade 11, we'll find out 2 of these reactions don't actually exist. Alright, so the last reaction we're going to learn about is the combustion reaction, of which there are 2 types. Complete combustion and incomplete combustion. So the word combustion means to burn, while hydrocarbon refers to a special type of molecule, one that contains hydrogen and carbon. So these are typically fossil fuels like gasoline, octane, or natural gas, propane, butane, methane. We burn these fossil fuels for the energy they release. Well, that's the whole point of a combustion reaction, to release energy. Now these reactions follow a very set pattern. It doesn't matter what hydrocarbon you're burning, it always requires oxygen gas, it'll always produce water, it'll always produce carbon dioxide, and it'll always produce energy. So let's say I burn methane, CH4. Well, you're going to need oxygen to burn it because fire always needs oxygen. You'll produce water, you'll produce CO2, you'll produce energy. What if I don't want to burn methane? What if I want to burn propane? Well, you still need oxygen for that fire, and you'll still produce water, still produce CO2, still produce energy. No matter what hydrocarbon I burn, C3H8, or butane, C4H10, or octane, C8H18, C whatever, H whatever, you'll always need oxygen for that combustion reaction. You'll always produce water, CO2, and energy. So this pattern does not change regardless of which hydrocarbon you burn. Now the word excess means a lot of, more than you need. So if you have a lot of oxygen, if you have excess oxygen during this combustion reaction, we say it's complete combustion. So if you've ever seen a gas stovetop with a blue flame, they design these nozzles to mix the gas with the right amount of oxygen, excess oxygen, so you end up with nice, clean burning, complete combustion, where the only waste products are water and CO2. Problems occur when you don't have enough oxygen, or as we say, limited amounts of oxygen. Now complete combustion switches over to incomplete combustion, and that is problematic. You still make the same products, water, water, carbon dioxide, carbon dioxide, energy, energy, all the clean products of a complete combustion, but now you also get these toxic chemicals, carbon monoxide and carbon soot deposits. So for one thing, we like complete combustion because it gives off a lot more energy, and also it's clean burning. The blue flame of complete combustion doesn't really leave much in terms of carbon deposits, doesn't really blacken your pots and pans. Whereas incomplete combustion, where you don't have enough oxygen, leaves ashes, carbon soot deposits that will blacken your pots and pans. But the most dangerous part is the production of carbon monoxide gas. Carbon monoxide is toxic to us. Our bodies are designed to get rid of CO2, so that's not a huge issue. But they are not designed to get rid of carbon monoxide. If you breathe air that has oxygen and carbon monoxide in it, given the choice, the hemoglobin in your blood will always latch onto the carbon monoxide. It's much more attracted to carbon monoxide than it is to oxygen. Unfortunately, your body needs oxygen to survive. It doesn't need carbon monoxide. So you end up suffocating. I don't know if some of you remember this, but back in 2013, there was a huge ice storm in Ontario. It knocked out the power in much of southern Ontario. Without electricity, people started freezing. So what did they do? Some people brought in gas-powered electrical generators, and other people would just bring in their barbecues into the home. They would then burn the fossil fuels to heat up their homes. Now, at the start, there was a lot of oxygen in the house. Excess oxygen. So initially, these generators and barbecues were combusting completely, just producing water, carbon dioxide, and lovely heat to warm up the house. But overnight, with the windows closed, the oxygen levels in the house started to drop. As the combustion reaction started eating up all the oxygen, turning into water and CO2, now we don't have enough oxygen in the house. It becomes limited oxygen. And so complete combustion now becomes incomplete combustion, releasing deadly carbon monoxide gas. Sadly, several families in Toronto went to bed warm, but never woke up. They suffocated from carbon monoxide poisoning. So it's very important that you do not burn fuels inside the house unless they are properly ventilated so you can get excess oxygen to the combustion reaction. Well, that was depressing, but hopefully you have learned something from this tragedy so that it does not happen to you. But with regards to tests and assignments, I will tell you in the question itself whether or not it's an excess or a limited oxygen scenario so you know which equation to write out.